We're going to do a little bit of reviewing of some of the earlier stuff and just kind of roll through some of the ideas and stuff that we talked about, the kind of highlights here as our finals come in. In that sort of first chapter, really wasn't very much there. So we really got going there kind of into chapter 2-ish, I think. And in chapter 2, we talked about obviously measurements, right? And uncertainty in measurements. Remember that any measurement that you take, there is some degree of uncertainty. And as we talked about, you know, if you had something like this, these were centimeters and you're rolling this way, you want to think about how many dashes you have between the numbers. In this case, that is 10 dashes, which means each one represents 0.1 centimeters. You could also divide your smallest guy by 2, which will give you really how far you can take these readings, right? And in this case, you usually could go one more place to the smallest digit. So this would be obviously be 1.1, 1.2, 1.3, and about 1.4 in this case. We would want to record one more because we can do that in this guy and also here, as we talked about, right? We always record all the certain numbers. And that first uncertain number. And that is obviously what we refer to as Sig Figs, which was a pretty big part of really this chapter here. And when we talk about significant figures, we are talking about things that are non-zeros, right? Will be significant. Zeros in terms of leading zeros are not significant. Zeros that are trapped between two numbers are significant, and zeros at the end may or may not be significant. In this case, not significant. But if you put a decimal point there, for example, now all these guys are significant. So it is that decimal point right in the number that makes any zero at the end significant. You also want to make sure that when you're writing numbers, as we talked about, obviously in something like scientific notation, all the numbers before the times 10 part are significant, right? And if you kind of go between the two, as we talked about, you don't want to lose any obviously significant figures along the way. You should maintain obviously your sig figs as you go from one place to the next there. Any questions on that there? We also talked obviously a lot about calculations and sig figs. And remember, the two kind of main things that we do is we either will multiply or divide. And here we look at the smallest number of sig figs is what your answer should have. And obviously when we add and subtract, we are looking at the smallest number of decimal places. So again, remember that if you're doing some type of combination of all those things, as we've talked about many times, you pretty much don't want to round to the end, but you want to keep track of everything along the way and really clean it up at the end with the final sort of calculation that you do. Also in this chapter, really a big part of this chapter was conversions, right? And dimensional analysis. And that is where we take any type of equality, like 12 inches equals 1 foot, and we obviously can write 2 conversion factors for them. And when we do something like dimensional analysis or conversions, you know, if we had 325 inches and we want to know how many feet, we always, as we should be doing, right, showing it where the units will cancel each other out. And calculator, I guess we could actually do that. 325 divided by 12 in this case gives us something like 27.08333 feet. In terms of significant figures, this is what is considered, right, an exact number, as it is basically English to English conversion. So we would default back here to 3 sig figs, which would come here. Looking at this number means we should get something like 27.1 feet in terms of the proper number of significant figures. Remember that when you're using any type of conversion factor, there's the two systems of units. There is English to English units, and there's metric to metric units. And remember that if it's like an English to English or metric to metric, it's all considered an exact number, which can have as many significant figures as you want, which means we ignore it typically in calculations. It's only when you cross over from kind of English to metric that you do have to look at the number of significant figures. If it's not an exact conversion, there are a few that are, like 1 inch is 2.54 centimeters. But, you know, if you maybe use something like 1 pound is 454 grams, it's really not the exact number. You should look at the sig figs in that conversion factor, and it would be obviously the number, not the one part of it. So there'll always be a 1 in those conversions, and it's the number part that you would look at. Any questions on that there? Now, also in this early chapter, we talked about density, right? And density is basically the mass to volume, right? And that is D is equal to M over V, which obviously we can rearrange and solve for V is equal to M divided by D. Or if we want the mass, it would be the volume times the density. Typical units of density are grams per milliliter, are grams per cubic centimeter, and a reminder that a cubic centimeter is the same as a milliliter. Cubic centimeter is how you get it when you kind of take a length times a width times a height measurement. They are all length measurements, but when you multiply them together, that gives you a volume in that particular case. We could obviously use this as a formula and solve for any of those things: density, mass, and volume. Also remember that very common procedure in density is volume by displacement, right? You put a solid object into some water or something like that, it will cause the water to rise, and it will displace a volume equal to its own. So the volume of the object is usually the final volume minus the initial volume. And again, that's a very common way, especially with density, that we do solve for the volume of a particular object. The last thing that we talked about was, or in this chapter coming to my mind is, we talked about metric and prefixes, right, that go with it. And then remember that you want to make sure that you do use the prefixes correctly, like kilo, right, is 10 to the 3. So what that means is that's how many of the base unit there are in one of the prefix units. So in 1 kilogram, which is the prefix unit, there would be 10 to the 3 grams, not the other way around. Again, that's a very common, as we talked about many times, sort of mistake that people make. They sort of reverse those guys. I think that's pretty much chapter 2 there. Any questions on that there? Okay, then we rolled into chapter 3. Let me just take a look real quick here. I think that's what that stuff's about. All right, so chapter 3 was a pretty short chapter. We got into really states of matter. And obviously we have solid to liquid to gas. And obviously in the solid state, things are put together pretty tight to one another. In the liquid state, there's a little bit more room for movement, but still relatively close to each other, which is why liquids are fluid. And then obviously, as we go into the gas phase, everybody has broken apart from one another. The changes of phase here, solid to liquid, again, that is what is referred to as melting. Going from liquid to solid, that is freezing. Going from liquid to gas, that is evaporation or vaporization. Going from gas back to liquid is condensation. And obviously going from solid, skipping the liquid part, is sublimation. and heading in the opposite direction. I'll go this way, going from gas back to solid, skipping the liquid part. That is deposition. And we talked a lot about energy in the next chapter, but in terms of energy here, as we go from solid again to liquid to gas, those are all endothermic processes, which means heat and energy is being absorbed. And as we go in the opposite direction from gas to liquid to solid, that is exothermic, which means you need to release all that heat and energy. Everybody will slow down and basically come into those different sort of phases. Also in this chapter, we talked about pure substances that can either be obviously elements or compounds. And remember that there is a difference between compounds and molecules. Molecules, again, are just a basic definition that two or more atoms are together. They could be the same, right? Because we could have something like H2, which is both an element and also a molecule because there's two of them together. And we could have something like H2O, which is a compound and also a molecule, because also there are two or more atoms together. Again, water would not be an element because it's obviously more than one element together. So for it to be an element, it's just got to be that one guy, but they can be molecules. There's a lot of diatomic molecules, right? Which means there are two. And that is our hydrogen, oxygen, nitrogen, and pretty much all of our group 7s are fluorines, chlorines, bromines, and iodines, right? They all come basically as twos. In relationship to pure substances is that we had mixtures, right? And a mixture is really a combination of two or more pure substances that maintain their identity. So if you take two or more pure substances basically and mix them together, you will get a mixture. And a mixture could really be one of two different types of mixtures. We can have either a homogeneous mixture or a heterogeneous mixture. And in terms of that, here at those two, we could have a homogeneous or a heterogeneous mixture. And in a homogeneous mixture, everything is the same throughout. It basically means that they will all mix together. So if you took some salt and you took some water, which by themselves are pure substances, and put them together to make salt water, it would be a homogeneous mixture, right? We won't see the salt anymore. It will dissolve into the water part of it. A heterogeneous mixture is we still see different phases, or layers is sometimes referred to. That, for example, if you took something like, say, sand and water. So again, both of those are pure substances. And if we put them together, we will get obviously sandy water there, sand plus water. And obviously you could do what you want. That sand will never dissolve in there. You'll still see it as part of the mixture. Now, remember, regardless of the type of mixture, regardless if it's a homogeneous or a heterogeneous mixture, you can't separate them out. So filtration we talked about is done to obviously separate a solid from a liquid. That's a good way of doing that. And to do that, obviously, you've done it many times throughout the semester, but you take obviously a funnel, a little piece of filter paper, right? You pour your mixture in there. All of the solid gets trapped on the filter paper. And obviously all the liquid part goes through there to your beaker that's going to hold it. And that's a really good way to separate out a lot of times a solid from a liquid, like a lot of heterogeneous mixtures might be. You could also separate out a homogeneous mixture like salt water through a process known as distillation that we talked about. Basically, you did sort of a version of this without the collecting of the water part of it. But again, if you took that salt water and you heated it up, that's going to cause the water to start to evaporate, which it has nowhere to go. And if you keep this really cold, this connecting tube, it will cause that steam to basically come back to liquid water, and it will go through condensation on the other side. And if you continue that process, eventually you'll evaporate off all of your water, and you will be left with just the salt on the left-hand side and the water on the other side. We did this a couple experiments, I think, with more of a evaporating dish where we let the water obviously go out into the sky there, and we didn't collect it, but you were left with some type of residue that was in there. That is why a mixture is a physical change, yeah. And that's because there is nothing that has fundamentally changed. You could get back all of your original components. And that's the hallmark of a physical change, which we also talked about in this chapter, which is basically what you start with and what you end with is basically the same thing. It may look different or something of that nature, but it hasn't fundamentally changed into anything that is different. And that's different than a chemical change, where what you start with and what you end with are different things. And the important part of that is you cannot do any type of physical means like boiling, freezing, filtering, whatever it may be, to basically separate out and get those original guys back. You have to do some type of chemical change to do that. Most chemical changes are chemical reactions, is basically where we see that. You know, so again, if we took our hydrogen gas and oxygen gas to make water, that would be a chemical change. You could take water and do a bunch of physical things to water, but you'll never get back the original components, the hydrogen gas or the oxygen gas, unless you do some type of chemical change to it. You can do that. And you did that with the battery, the 9-volt battery, and the electrolysis of water. You were able to create hydrogen gas and oxygen gas when you basically cook that thing up. So you can, through chemical means, take a compound back to its elements, but again, some type of chemical process there. But you cannot obviously go any further, obviously, than elements. That's pretty much as far back as you can go. Any questions on any of that stuff there? Hopefully it sounds familiar. I hope some of this. All right, then we rolled actually up the book there to chapter 10, where we were talking about energy. So let's talk a little bit about the energy chapter there that we talked about. So I think that was chapter 10. Some energy. So obviously two really important units of energy that we really talked about most are joules and calories, and these are calories with the lowercase c. We also talked about nutritional calories, which have the capital C. Other variations of those units are kilojoules, which is also a very common unit of energy, and kilocalories. And there is in 1 kilojoule 1,000 joules, and obviously in 1 kilocalorie there is also 1,000 of the little calories as well. The relationship between those two we also use in 1 calorie. There is 4.184 joules, right? And a good way to remember that is that's the specific heat of liquid water, right? So that's where that number basically comes from. So remember that we do have the conservation of energy, which means we do not create nor destroy energy, but it can be transformed from one part to the next. And there's different types of energy, like the classic potential energy, right? of that guy that is sitting on the top of the hill, the boulder. And obviously, as it moves down, it maybe falls over, it can be converted to kinetic energy. And when it hits the ground, it will transfer a lot of that energy to the ground or whatever is standing underneath it. And it will come to rest, obviously, at a different potential energy at the end. Remember, we think of energy sort of as a perfect exchange. So whatever energy somebody loses, somebody else will gain that energy. And really, when we talk about energy, there's two important types of reactions that we talked about, which is exothermic, which means our heat and energy is released. And there are two ways that we will see these guys, which is Q, which is heat, and that typically is a negative value, and delta H, which is our enthalpy, is a negative value as well. So pretty much a negative value for energy means that it's exothermic, heat and energy is being released, and that is opposite of endothermic, where heat and energy is absorbed. And our values for Q would be positive, and our value for delta H would also be positive. Speaking of delta H is the enthalpy of a reaction. And one way that we could calculate delta H, which is very common, because energy and delta H, which is energy, is a state function that we talked about. Remember that state functions, the only two things that are really important is where you start and where you finish. And in a reaction, where we start and where we finish, right, is we start at our reactants and we finish at our products. And that's why a lot of this sort of energy, like delta H, can be simply calculated by taking the delta H value of your products minus the delta H value of your reactants. And those are typically values that you would find in a table. And when you go to that table, as we talked about, it's really important to make sure that you find what you're looking for and that it's in the correct state. You know, if you have something that's a gas, a liquid, or something that's aqueous or a solid, it may have different values depending on the state. So you want to make sure that you do find sort of the correct one. The other important thing is, if you were just to ask what is the delta H of a reaction and you got something like this, you would calculate the delta H of this reaction by taking our products, and you also got to take the coefficient into account when you do that. So that would be 3 times the delta H value that you would find in a table for C. And you then would subtract it from all of your reactants, where you would take 2 times the delta H value for A that you would find in the table, plus 1 times the delta H value for B in this particular table, whatever that may be. And again, that will give you either a positive or negative value for the delta H of the reaction. And that will tell you, obviously, if it's an endothermic or exothermic reaction overall. Any questions on that there? The other sort of thing that we also talked about in this chapter were those energy diagrams, which I think we revisited not too long ago there. But just to remind you of what those look like, they do look different, whether or not they are an exothermic or an endothermic type reaction. And again, when we look at those energy diagrams, and this is the reaction that's progressing, we have our reactants to our products. And again, that hill that everybody has to climb, as we talked about, I think maybe the other day, was the activation energy. And again, that is basically the hill that the reactants has to climb to get to the other side. But in this case, our reactants are higher in energy than our products. So in order for it to get down there, energy is released, which means this is an exothermic diagram. And again, when we're doing that delta H calculation, it is the difference between where the products end up and where the reactants started is how we do that. And that's why, again, we do our products minus our reactants. Remember, our endothermic diagram looks a little bit different. And that is where we have our reactants to our products there. And once again, as we talked about, I think the other day, you could see again that our activation energy here is much larger, and that's because energy's got to be put in to help everybody get up and over that much larger hill to get to the other side. And again, if we were doing our delta H here, it would be the difference between those two guys where they end up. And again, that would lead us to a endothermic reaction where our delta H again would be positive and our delta H here would be negative. Questions on that there? We also talked about, I think in here as well, the idea of a catalyst, right? And a catalyst can speed up a chemical reaction. Remember that it is not a reactant, is not a product. It does not get used up in the reaction. It is there simply to allow the reaction to occur faster. And what a catalyst basically does, if we borrow this diagram, is it will lower the energy of activation. And by lowering the energy of the activation, it allows basically that reaction to occur a lot faster. We also talked about in this chapter here specific heat capacity. And the specific heat capacity is the energy needed to raise 1 gram of a substance by 1 degree Celsius. This is the guy that has units of joules per gram per degree Celsius or calories per gram per degree Celsius. The important number, right, for the specific heat of liquid water is the 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. And that's a number obviously is used a lot. There's an equation that we talked about that we use, which is our Q is equal to ms delta T. This equation is used when we are in the same state, but we're changing the temperature. So as long as you're in the same state, but the temperature changes, we do use this equation. The Q here is heat, and that is either a joule or a calorie in terms of units. M is mass, which is in units of grams. S is our specific heat capacity, which is in one of those units. And then obviously here our delta T, as we talked about a number of times, it's really important to do your final minus your initial. And this is typically, in this case, degrees Celsius. So this is one of the cases, rare cases in chemistry where you don't typically have to convert it to Kelvin. So you can use Celsius here. And it is that change in the temperature, which is really the only thing that will give us either a positive or negative value. And just like before, you get a Q that is negative, that is exothermic. And once again, a Q that is positive would be endothermic. And actually, if you do this type of experiment like we did in lab, where we used the coffee cups and the lid, and we basically put stuff in it. If you do this, Q at constant pressure is equal to really the delta H of the reaction. So if you did a constant pressure, which is in most cases, you can actually calculate the delta H of that particular reaction. We also talked about the idea that we can transfer energy from one object to the next. Kind of like what you did when you heated up the metal pieces and you threw it into the room temperature water. That water is going to absorb all that energy, right? And the metal is going to release all that energy. And in a situation like that, the Q of the water will equal minus Q of the metal, right? So that's one way very commonly that we could just use water, follow the change in the water, and we could figure out how much energy was either absorbed by the water, which means that's how much energy was released by the reaction, or vice versa. If how much energy the water lost would be how much was absorbed by the reaction. So again, you can use it for either way, exothermic or endothermic. Whatever anybody is losing the energy, And whatever energy somebody gains will be the same numerical number, but the signs will change, right? One is negative for exothermic, whoever's losing it, and one is positive for endothermic, whoever is gaining it. Any questions on that there? I think we also here talked about Hester's Law, which is the idea that not all of reactions occur in sort of one step. You know, maybe it happens in multiple steps here. And for each of these steps, we could have a delta H value. We'll just call this plus 100 kilojoules. And for this guy, we'll call it minus 50 kilojoules. So if we were to add these reactions together, anything on opposite sides of the arrow would cancel out. So the C on both opposite sides would cancel, also would be the D's. This would give us our overall reaction. A plus B goes to E plus F. And if we want the delta H for this reaction, we would simply add these two delta H's together. And in this case, it would be delta H1 plus delta H2, which would give us 100 plus minus 50. We can try that without the calculator and go with 50 kilojoules in this case. And that would give us a positive value for this reaction overall, which means it would be endothermic. Remember, though, if we need to do something to one of these reactions, which you commonly do need to do, you do have to change the delta H value. So what happens if we needed two of maybe A? We would have to multiply that entire equation by 2. And what that does to the delta H is we would also multiply the delta H value by 2. And for this reaction, it would be 200 kilojoules. If we needed to reverse the reaction, maybe we need C and D on the other side, and we need A and B on the product side. When we reverse the reaction, we change the sign of delta H, so it would become negative 100. And lastly, usually you might need a divide. So if we divided by 2, to get back to our original guy, we would divide this guy by 2, and that would bring us back here. So if you have to reverse one of these reactions to get it into the right sort of positioning, you change the sign of the delta H value for that reaction. If you need to multiply by a common number to get the correct numbers, you multiply the delta H by it. And if you need to divide by a common number, you divide the delta H by it. The important part of this when you're doing something like Hester's Law is just to get everybody on the right side in the right amounts and make sure you keep track of what you did to it so you can keep track of the delta H values so you know what you will have to do. And then you basically just add them all together when it's all said and done. So that's the important part here. Any questions on that there? All right, so I think that was pretty much 10 in that case. Then we rolled back to chapter 4, I think, after that, and just take a quick shot at chapter 4 here. All right, so into chapter 4, it was all about the atom, I believe. So we talked about some important experiments along the way. We had Dalton's atomic theory, right? And the most important thing about Dalton is he went bowling on Thursday. There you go. But he also came up with the Dalton's atomic theory, the idea of what an atom is. And not all parts of it is correct, as we talked about. And 2 main parts is really not sort of correct still today. And that is the idea that all atoms of the same element are identical. And the existence of isotopes, for example, where they do have different numbers of neutrons, means that that's not correct. The other part of it is that not all atoms are indestructible. So you can't, through, say, a nuclear reaction, sort of change it into something else. So this idea that atoms are not indestructible and the idea that they're not all identical atoms of the same element are 2 things that really don't hold up. And that's the idea of a theory. It may be right in some aspects, but also may be incorrect in others as you go down the road. Most of a lot of important work in terms of the atom, which obviously contains electrons, protons, and neutrons, right? Started with the cathode ray tube, right? And we had two sort of important experiments in there. We had Thomson and Milligan. And Thomson did experiments with the CRT tube and came up with the charge to mass of an electron, while Milligan did the oil drop experiment, where he came up with the charge of an electron, right? And from those two sort of experiments, really the mass of an electron was able to be determined as 9.09 times 10 to the minus 28 kilograms in that case, which is a really small number. It came out of that as well, along with some future sort of ideas and experiments, was the idea that the atom was basically neutral. So they sort of discovered electrons, but really believed it had a positive sort of idea. And that came to an early model of the atom, which was the plum pudding model. And that is a atom where there is basically positive charge distributed out through the atom. Embedded inside of it are these electrons, and most of the mass of the atom was the electrons. And this was really sort of the accepted model from Thomson for many years, until really the next biggest sort of discovery there in terms of the atom came about, and that was Rutherford and his gold foil experiment. And Rutherford and his gold foil experiment basically shot alpha particles, which are positively charged particles, basically helium particles, at gold foil, which is hence the name, the gold foil experiment. And what they expected to happen based off of this model was, because they are positively charged, because that's all a dense sort of spread out, not really dense, but really a spread out positive charge there. They expected them to go through because they're moving fast, but there should be some deflection that sort of would occur. And Rutherford was really surprised that when he shot his alpha particles at pieces of gold foil, he pretty much saw them mostly just go straight on through with no problem. But every so often he did see alpha particles get bounced off at these really large angles. Some of them would even come back to the source it came at. And as we talked about, in order to make something that's positive and kind of heavy and moving really fast bounce off at that, it also had to hit something with a very similar charge, right? So positive and positive things don't like each other. Negative charges and negative charges don't like each other, but positive and negative things are attracted to each other. So they kind of had to throw out the plum pudding model and say that the atom here was mostly empty space, which accounted for why a lot of those alpha particles just sailed through with no problem. But it did contain a dense positive core, which they called the nucleus, and later found, obviously, that protons, which are positively charged, are found in the nucleus. And later in 1930s, it was discovered that neutrons that have no charge also found in the nucleus, and that most of the mass of the atom is actually the nucleus. And that also made sense based on further sort of experiments, because out of our protons, electrons, and neutrons, it is the neutron that is the heaviest particle. And the electrons are actually the lightest. And the proton is pretty close to a neutron. They're very, very close to each other in terms of mass. And that makes sense because, again, protons and neutrons found in the nucleus, they are, again, going to be our major contributor to the mass of it. So our sort of model of the atom now is our nucleus with our protons and our neutrons, our electrons moving about in a random pattern here around the nucleus. It obviously going to be attracted to the nucleus because it's positively charged, and electrons are negatively charged. Any questions on that there? In this chapter as well, we got into, I think, a conversation about atomic numbers, right? Which is abbreviated with a Z, and that is the number of protons there are in an atom nucleus. Remember that the atomic number can be found on the periodic table. That is the number up on top. Every element has its own atomic number, which means if you know the atomic number and the number of protons, you know what element you are talking about. And also remember that it will tell you the number of electrons there are if it is a neutral atom. So if it's neutral, it will also tell you the number of electrons. But the definition of atomic number is just the number of protons. So that is the actual definition of it. The other number that was important that we talked about was the mass number. And that's sometimes abbreviated with an A. And that is the number of protons and the number of neutrons there are. And if you take the mass number and you subtract it from the atomic number, that will give you your number of neutrons. So mass number minus atomic number will give you a number of neutrons. Remember that when you calculate the mass number, the atomic number, protons, electrons, and neutrons, they're all positive whole numbers. That is also why the mass number is not on the periodic table. So a reminder that the number on the bottom there is not the mass number. That is the atomic mass that we find on the periodic table. So we also write these guys in an isotope form where we put the mass number top left and the atomic number on the bottom left there. Every element has protons, electrons, and neutrons except for hydrogen, which has only a proton and an electron. It does not have a neutron. And we could have isotopes. Remember, like for hydrogen, that is hydrogen. That is deuterium. And that is tritium. Those are all really hydrogens, but they have different names. These are isotopes because they have different numbers of neutrons. In this case here, 0 neutrons. This case here, 1 neutron. And this case, 3 minus 2 is 2 neutrons. So because they all have different numbers of neutrons, they have different masses, which is why Dalton's atomic theory is not correct in that sense, because they are all still hydrogen, because they all have 1 proton in this case. Top number minus bottom number gets you your number of neutrons when you write it like that. Also, if you have a number that is written like this, or an isotope that's written like this number again is the mass number. So you could get the atomic number from the periodic table there. Any questions on that there? Things that have charges, which are obviously ions, right? Things with charges. And there are cations and there are anions. And obviously cations lose electrons and anions gain electrons. So if you do have something with a charge, for example, like sodium 2211 with a +1 charge versus say sodium 2211 with no charge, this sodium with no charge would have 11 protons. 22 minus 11 would be 11 neutrons. And in this case, it would also have 11 electrons. 11 positive guys, 11 negative guys give us 0 charge. When we get to a plus charge here, this guy has still 11 protons, still has 11 neutrons, but electrons here, it actually only has 10. 11 positive charges, 10 negative charges is where our +1 charge comes from. So if you're doing any of these things with something that has a charge, the only thing that changes is the number of electrons. And that is because if we change the number of protons, we will change the element. So it is just the number of electrons that change. Any questions on that there? Okay, and I think in this chapter as well, we were introduced officially to the periodic table. So hopefully we remember the periodic table as we've seen it many times, I think, throughout the semester. If I can learn how to count, that would be good. All right, so obviously heading down on the periodic table is a group. right? Down a column. A period goes left to right, and there's also 7 periods there on the periodic table. We have group 1, which is our alkali metals. We have group 2, which is our alkaline earth metals. We have some group. We have group 7, which is our halogens. We have group 8, which is our noble gases. We have a staircase that kind of comes down this way. And to the left of the staircase, right, are metals. Above the staircase and to the right there are non-metals. And the staircase itself, which kind of works its way down, are sometimes referred to as metalloids, right? Metals are shiny, they're good conductors of heat and electricity. Non-metals are pretty much the opposite, dull, brittle, not good conductors of electricity. Metalloids basically fall between the two. The same metalloid could have properties that are similar to metals and also have properties that are similar to non-metals. In between group number 2 and 3, right, that is our transition metals. And those are our guys with multiple variable type of charges. 2 rows at the bottom, right, are actinides and lanthanides because they technically go right about there in my badly drawn periodic table. And these are also sometimes referred to as intertransition metals because they kind of go there in that spot. I think that's most of that. Any questions on that? Since we talked a little bit about charges, a reminder, common charges +1 when they do make a charge there, everybody in group 1, +2 when they do, +3 here, which is really aluminum. -3 for our nonmetals in group 5, -2 for our nonmetals in group 6, and -1 for our nonmetals above the staircase there in group 7. Remember, our transition metals have a variable type of charge. There are 3 exceptions, zinc and cadmium, which is right around in this ballpark. They will always make a +2 charge. And I'm running out of room, so I'll just put a little dot there. Silver there will always make a +1 type charge as well. So those are 3 sort of guys that will have fixed positive charge. Everybody else there in really the transition metal region. And also those metals that fall below the staircase as well, like lead and tin and antimony, they could have a variable charge. Also important to note that, as we talked about a number of times, things do not have charges, right, until they basically hook up metals and non-metals. That's when they get charges. If you have something like iron by itself as a piece of metal, it does not have a charge. Any questions on that there? I think that's chapter 4. All right, then we went off to chapter 11 in our journey of waves and electrons, I think. So chapter 11 here, you can go with just electrons, I think. Electron configuration was the big topic in that chapter, but it really did start a little bit with waves. So we talked about waves at the beginning there, and our wavelength, which is lambda, is the distance between 2 peaks or troughs. We also have the amplitude of a wave, right, and the speed of a wave. There is a couple of formats that we saw, which is C is equal to the wavelength times the frequency. That's what the nu stands for. It looks like a V. And this is the speed of light, which is a constant, 3 × 10⁸ meters per second. This is our wavelength in meters, and this is our frequency in reciprocal seconds. And remember that a reciprocal second is the same as a hertz. So those guys are sort of interrelated to each other. We also talked about the idea that energy is transferred through space in the form of waves. We kind of related this to electrons, right? As they go up in energy, they gain energy. And obviously, as they drop back down in terms of energy, they have to give off that energy in the form of a wave. And there is one way that we could calculate the energy of a wave is E is equal to h times the frequency. H is Planck's constant, 6.63 times 10 to the minus 34 joule seconds. And again, our frequency is obviously still our frequency there of reciprocal seconds there. We could also solve this top equation for frequency, and the frequency would equal c times the wavelength, which is why sometimes you will see this equation written E times h times c divided by the wavelength, which means that if you know just the wavelength of the light that you're talking about, you could figure out the energy associated with it. Or if you know the frequency, you could also figure out the energy associated with it. So that gives you a little bit of variation in terms of how you could do that. We sort of, again, like I said, sort of related this to electrons as they transition from one energy level to the next, either absorbing energy or giving off energy in terms of this. And we also talked about the idea that depending on where that wavelength falls in the electromagnetic spectrum, we may see different effects. So on one side, for example, we have radio waves, we got some microwaves, we got a little bit of IR, we got the visible part of the spectrum, a little UV, some X-rays, maybe some gamma rays over here. Remember that the relationship between wavelength and energy is, on this side, we have a short wavelength, which usually corresponds to a high energy and also a higher frequency. On the other side, this is a longer wavelength, which usually corresponds to a lower energy and a lower frequency as well. So the visible part of the spectrum is really where we see color, right? That is where we see our Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. And even with the colors, there's energy differences. Red is actually lower in energy than, say, the violet color. That's higher in energy. And that also means that violet is a shorter wavelength than red as well. The color of light that we actually see is the complementary color to the light being absorbed. So the wavelength being absorbed is complementary to the color that we actually do see. We tied this into really the idea of electrons, and we talked a little bit about Bohr's model of the atom, and really Bohr's model of the atom worked really well for hydrogen and one electron, but it doesn't work very well for more than one electron. If you remember, Bohr's model of the atom is that planetary model where we have kind of the nucleus, and then we have these rings of orbits where electrons were traveling. And basically, we could ID the line spectrum that we see, which, as we also talked about, is what we see with elements, is this line spectrum of different colors at different wavelengths. We could basically satisfy that based on Bohr's model of the 4 lines that we see in hydrogen based on the transition. And that is n. N is the principal quantum number, which is basically the energy level. And when you have n equals 1, that is the ground state, which is the most stable, closest to the nucleus. Anything above that, like 2 through 7, they're sometimes referred to as excited states, which are higher in energy, further away from the nucleus. And really, as electrons sort of transition, it's going to give off those energy that can fall in that visible part of the spectrum where we will see colors. Now, as we get more electrons involved, we really sort of moved away from this idea of Bohr's model of the atom to a more quantized idea. And energy is oftentimes referred to as being quantized. And basically what that means is energy is really given off as whole packets of energy via this equation. And what that basically means is sort of like the staircase example that we talked about. you know, as you walk a staircase, and like electrons, you either find yourself on this step, this step, this step, or this step. You do not usually stop in the middle. And electrons will either gain enough energy to fully get to one energy level or lose enough energy to get down to another. They won't find themselves in between. And so they'll do those full sort of transitions. So moving away from Bohr, we moved away from the idea that electrons were housed in these known orbits as they're just prettily circling the nucleus, to this idea of orbitals, which are these mathematical theoretical descriptions of probability maps of where electrons can be found. And we talked about a few different types of orbitals: S, P, D, and F orbitals. And they all do have different shapes, like S is a circle, a P is like a figure eight, a D is a couple of figure eights together, and so forth. Now, the important thing that we talked about this is the idea that, like, on the first energy level, there is really just a 1s orbital. When you get to the second energy level, there's a 2s orbital and a 2p orbital. When you get to the third energy level, 3s, 3p, extra box there, it shouldn't be. And that is where we see our 3D. When you get to the fourth energy level, that is where we start to see our F orbitals occur. We have our 4s, our 4p, our 4d, and 1, 2, 3, 4, 5, 6, 7, our 4f. There are different numbers of each of these s orbitals. There are only one type of s orbital. P orbitals, there are 3 types of p orbitals on every energy level that has them. D, there are 5 types on every energy level that has them. And F, there are 7 types. And each individual orbital could only hold a maximum of 2 electrons, which means if you max out the s orbital, you could put 2 electrons in there. If you max out the p subshell, it's sometimes referred to, all 3 of those p orbitals together, that's going to be 6 electrons. If you max out the d subshell, that's 5 times 2 is 10 electrons. And if you max out the 7 subshell, that is going to be 14 electrons if you put it all in there. Remember that when we talk about a shell or a level, we're talking about all the orbitals that are there, which means this guy could hold 1 and 2, 3, 4, 5, 6, 7, and 8 if you max out that entire thing. We're talking about just a subshell. We're talking about a group of individual orbitals that make up the same guy. So this guy would max out at 10 electrons in there. Any questions on that there? With this, obviously, we talked about electron configuration, and really the easiest way to do it is just to make your little chart. Remembering that on the first energy level, that is where 1s's start. Second energy level is where p's start, and then you just copy down the number. Third energy level, that is where d's start. And the fourth energy level, that is where f start. And this is the order that gives you your electron configuration. And you just keep following the arrows until it's all filled out. So if you had something like lithium, which is 3, that would be 1s2, 2s2, 2s1. If I know how to count there, that would be better. 1s2, 2s1. If we count up the top numbers, that is 3. And that's the total number of electrons that there are. If you had something like sodium, which is 11, that would be 1s2, 2s2, 2p6, 3s1. We also talked about shorthand. That part of it there is 10 electrons, which is neon's configuration. And you could do sort of a noble gas configuration by shortening the electron configuration. As we talked about a second ago, sodium had, with a +1 charge, has only 10 electrons, which means you do need to adjust the electron configuration to reflect that. One difference, couple difference in electron configuration is copper and chromium. Copper's got 29 electrons. Chromium's got 24 electrons. I won't write the entire thing. Maybe I will. Let's see. We'll do argon 4s1, 3d5 for chromium, and argon 4s1, 3d10 for copper. Now, the exception happens here. It has one extra electron in the d orbital, one less electron in the s. It makes it more stable that way. The other thing that I think we also talked about is transition metals when they lose electrons, like iron, for example, which if we did just iron with no charge, it would be argon 4s2, 3d6. Iron with a +2 charge, it will actually lose the s electrons first because they end up being higher in energy. So this would be argon 3d6 in this case. And all transition metals are different than regular metals because they will always lose those s electrons first because they end up actually being higher in energy. So a reminder that when electrons go in, say, to the s orbital, they actually go into the s first and then into the d. But what happens is as you start putting electrons into the d, there's a switch in energy that occurs after they fill. And actually the s orbitals there are actually higher in energy. So those are the ones that are lost along the way. We also talked about drawing what is referred to as the orbital diagram for these things. So the orbital diagram here for lithium would refer to boxes or lines where you label it and you put arrows, right? First one up, second one down, never in the same direction, and first one up. Obviously, when you get to something like we talked about, like the p orbitals, you should have basically 3 boxes that represents 2px, 2py orbital, 2pz orbital. They fill by doing one at a time, maximizing the parallel spin, and then they come back and start pairing off. So that is the proper way to do that when you do those orbital diagrams. Any questions on that there? That I think is chapter 11-ish, I think, for the most part. All right. We will lay it up there for now, I think.